come back. At first, Happy Teacher's Day. In this auspicious Teacher's Day, at first, my sincere pranam to my Gurudev, Thakur Ma Swamiji. Then, my sincere pranam to all my teachers and my parents. Your guidance and mentorship have saved me. I am grateful for your unwavering support. So, again Happy Teacher's Day. Today I will discuss some few topics because today Teacher's Day, but this topic is very important. So, please take some time out and try to learn this topic and make the points and save this video with you and keep watching it every small interval. Then you will understand it in better way. In this video, I have defined Cauchy sequence and what is the complete metric space. And in my previous video, I have defined Banach fixed point theorem. Today I will discuss this topic elaborately. We all of us know Cauchy sequence means if xt be a metric space, then a sequence xn is Cauchy sequence if for all epsilon greater than 0, there exists one capital N belongs to natural number such that for all n m greater than equal to capital N, distance between xn and xm less than epsilon. And the metric space xd is complete if all Cauchy sequences are convergent. Okay? We all of us know this part. In my previous video, I have defined the Banach fixed point theorem. This is actually goal of my previous video. And we all of us know the statement of this Banach fixed point theorem. Banach fixed point theorem always defined in complete metric space. That means here every Cauchy sequence is convergent. And here the mapping defined, since here I have defined the metric space x comma t, and here the mapping defined x to itself, and mapping is contraction mapping. All of us know what is the definition of contraction mapping. Distance between the image point means here, since I have defined the mapping as a t, so distance between the image point tx comma ty always less than equal to alpha times d of xy, where this xy belongs to the metric space x, and this alpha always lies between open interval 0 to open interval 1. This is the condition of contraction mapping. Then by Banach fixed point theorem we can tell if this satisfies these two conditions, then there exists always one unique fixed point. Consider this point is x0. Then this satisfies d of x0 equal to x0. I hope my all viewers have understood what is the Banach fixed point theorem. In my previous video, I have proved this theorem elaborately. Today actually I will see some example, and these example actually very important for higher study. At first I will say some example of complete metric space. This type of example actually very important. First question, here the space is open interval 0 2, and here metric space is usual metric space. In this metric space, the set is not complete. Why not complete? Because consider one sequence 1 over n. Then distance between xn comma xm tends to 0 as nm tends to infinity. Okay? That means this sequence is Cauchy sequence, but this sequence converges to 0 but this point 0 does not belongs to this set. So the set X is not complete metric space. Okay? But if we consider the set X equal to 0, 2, then in this metric space, this set is complete. But if we consider same set, but metric space D is discrete metric space, then in this metric space, the set X is complete. Why complete? Because, so we all of us know, in discrete metric space, every Cauchy sequence is constant sequence. And in discrete metric space, d of xy equal to 1 when x not equal to y and 0 when x equal to y. And consider x and be a Cauchy sequence. Then take epsilon equal to half. Then obviously there exists a natural number capital N such that Nm greater than equal to capital N. Distance between xn and xm less than half. In discrete metric space, distance between xn and xm less than half means obviously x equal to y. Because here when x not equal to y, then the distance is 1, and when x equal to y, then distance is 0. Okay? That imply after some stage, after capital N, xn equal to xm, that means after some stage, all sequence are equal. And we all of us know this is actually definition of eventually constant sequence in discrete metric space. So, since here the Cauchy sequence are actually eventually constant, so this is obviously convergence. So, this set is complete metric space when the metric space is discrete metric space. I hope my all viewers have understood how the metric space is complete or not. This is depends on which metric space is indicate. Okay? Oh well. Our next example, I will see one example of Banach fixed point theorem. This example actually very important. This example, I will see one integration operator. Let's see the question. Lambda belongs to real number and two function fg belongs to C0ab and k belongs to C0ab cross ab. Then the question is, for which lambda the mapping T of fx equal to gx plus lambda integration a to b kxy fx dx. Is this mapping is contraction mapping? This is my question. For which lambda this mapping is contraction mapping? This question is very important but very easy. At first we have to prove this mapping is contraction mapping. For this, T f1x minus T f2x equal to integration a to b absolute value of lambda kx1 kxy f1x minus f2x dx, and this is obviously we can write this is less than equal to absolute value of lambda absolute value of kxy integration a to b f1x absolute value of f1x minus f2x dx. And this absolute value f1x minus f2x, this absolute value always less than supremum of f1x minus f2x. Then if we consider this is less than supremum of f1x minus f2x, then this is less than equal to absolute value of lambda since here I have considered this is less than equal to this part, here integration a to b absolute value of kxy dx, and this means actually the metric space C0, here the interval f1 f2, and here kxy, just integrate this part, this is b minus a. Okay, now consider this kxy equal to c, this is lambda dc0 f1 comma f2, this is c b minus a. Therefore this mapping is contraction mapping for those lambda which is less than equal to 1 over c times b minus a. I hope my all viewers have understood for which is lambda the mapping integration operator is a contraction mapping. Then since the mapping is contraction mapping, and obviously this metric space is complete metric space, we all of us know. So by Banach fixed point theorem we can tell there exists always unique fixed point. I hope my all viewers have understood this part clearly. Okay, here I will use the Banach fixed point theorem. Since by Banach fixed point theorem there exists unique fixed point, then this fixed point would be such type fx equal to t of fx and t of fx equal to gx plus lambda integration a to b kxy fx dx, where this f belongs to C0 ab, means set of all continuous function defined on closed interval ab. If G belongs to C1ab, means set of all continuously differentiable function which is defined on closed interval ab. If G belongs to C1ab, then that imply since fx equal to gx plus lambda, this part kxy integration a to b kxy fx dx, so that imply obviously fx belongs to C1ab. That means for this integration operator there exists one differentiable function. This is the fixed point of this operator. I hope my all viewers have understood this knowledge clearly. Okay, this is actually use of Banach fixed point theorem and contraction mapping. This type of concept actually very important for higher study. Okay, I will stop here because today is Teachers' Day. See you soon. Stay safe and stay positive always. Thank you so much.